We are now recording, so I did want to do at least one announcement. That's all I can think of right now. Well, I can think of a second one. I don't know the exact days and times on this, but if any of you, because you're some of our best math students, if any of you are interested in participating with the math team, and it's also sometimes called the math club, they meet on the Birmingham West Campus with Mr. Rossi, and I don't remember the times. It's, but you can email her if you're interested in participating. Her email address is njarasi, J-A-R-A-Y-S-I, at lawsonstate.edu. You got it? Yeah, you're going to participate, right? Yes. Okay. But it is a lot of fun, and there's some good competition coming up. I think it's in October. I believe it's when they do. And it's believe me, you're going to learn a lot of math in a fun environment and basically make your whole rest of your math career easier, okay? Because you're going to get all sorts of perspectives of math that will be very beneficial in the future. So please give it a shot. I'm going to try to find the emails. I saw them, but I didn't get a chance to open them. But I know she's recruiting students to participate. Okay. There is one other announcement, and this is one of those good news, bad news situations. The bad news is Monday's a holiday. It's Labor Day. No classes. The campus is closed. Okay. The good news is it doesn't affect us any because we meet on Tuesdays and Thursdays, so we don't lose a class. So you can rejoice with that. Okay. Any questions? Okay. So let's get started where we left off last time. And I think it was from this slide or somewhere thereabout. Any questions on anything we've done so far? Now, are any of you, yeah, you were not here last time. Did you get the course code? No. Okay. Okay. If you had listened to the YouTube video, you would have gotten it because it's there, but I'll put it on here again there. And let me find it. Okay, yeah. I haven't finished putting this class stuff on Blackboard yet. I'm going to try to get it there. I don't have but like 2 hours of office hours today, and one of those is lunch. And so, but tomorrow I have 4 hours of office hours, and I hope they don't fill us up with things to do so I can get some things accomplished. But I hope it'll be done. And then I've got some time over the weekend, hopefully, that I can work on it if I don't get it all finished tomorrow. So here's the course code. Let me get my pen set up. Okay. Lawson.al, I can't imagine what that stands for. And then when he sent it to me, it had a space. I don't know if the space is important or not, but it's 1139 and another space with a 2952. And for those of you who were here last time, that's what I gave you, right? Because I copied it from what I had it on to my roll book. And that's one reason I'm a bit behind. I had to get all the names off the temporary rolls onto the permanent roll, and I've got some big classes this time, and that took a while. Okay. So, any questions? All right. Now, I think we talked about, yeah, I'm certain we talked about this before, linear speeds and angular speeds. Linear speeds are measured, and I think in terms of units, length per time, miles per hour, inches per second, centimeters per second, meters per hour, whatever, kilometers per hour, whatever. Angular speed is measured in not length per time, but either radians per second, normally is the case, or you could have degrees per second or something like that. But it's angle per time, okay? The measure of the same, how is the central angle changing in time? Whereas linear speed is how far you're traveling per unit time. This is how many degrees or radians you're changing per unit time. Now, that led to example 6, and that's where we left off, but example 6 is not covered. So let's go back and do example 6 here. It's not on the slide set. Now, I don't draw circles well, but I'll give it my best shot. Let's imagine that's the face of a clock, with this being 12 o'clock here, 3 o'clock here, 6 o'clock here, 9 o'clock here, 1 and 2 somewhere in there, 4 and 5 somewhere in there, 7 and 8 somewhere in there, 10 and 11 somewhere there. Okay? And it doesn't matter where the hour hand is, and it doesn't matter where the minute hand is. But we're interested in the second hand. And here's the second hand here. And they tell us the second hand has a length of 10.2 centimeters. Okay, that's a length. Okay? The second hand of a clock is 10.2 centimeters long, as shown in my figure, or the one in the text if you got it. Find the linear speed of the tip of the second hand as it passes around the clock face. So if that's 10.2, and Jake decides to finally show up. Yeah, no problem. I know your situation. Okay. All right. Good deal. Glad you're here. And did you get the course code last time?
I did.
You did? Okay, good. It's back a slide or two. Okay? What we're doing, and this is a pretty ugly clock, isn't it, is on a clock, here's a second hand, and it says it's 10.2 centimeters long. Find the linear speed of the tip of the second hand as it passes around the clock space. So if we're looking for linear speed, remember what linear speed is measured in? It's going to be a distance divided by time. That's what linear speed is. Angular speed is angle per unit time. Okay? Let me hazard a guess that you must be Allison, right? Okay. Since you're the only other female in the class. Okay. I guess well. Okay, we're still missing Gavin and Chris. So hopefully they'll be coming next. All right. Now, they didn't give us very much to get either distance or time. So, how are we going to determine the linear speed? Make a guess.
We already know how the second hand moves at second.
Okay? Let's do it in a minute. How far does the second hand move in a minute? Second. Okay. It moves all the way around the circle. Okay? And what is that? The distance. That's called the circumference of that circle. And that's 2 pi r. There's r. All right? So, we do know the linear distance. That would be 2 pi times 10.2 centimeters. Now, how long does it take to get around the clock face? Second? 1 minute, or how many seconds? How many seconds? 60 seconds. So the time would be 60 seconds. So the standard unit for measuring time is seconds. You know, SI or U.S. customary. So we'll use that one. So this gives us 20.4 pi centimeters divided by 60 seconds. Okay? And pi being 3.1416 approximately, that's going to be something just a little bit more than 60. Okay? Well, 3 times 20 is 60. That's a little bit more than 20 and a little bit more than 3. So that should be something a little bit more than 1 centimeter per second. Someone punch it in and see what you see. In the South, we're pretty violent. We punch things in. In other parts of the country, they press things in. Okay, but we punch them, or we mash them. Sometimes we mash them. You know, but they press. Okay, literally.
0.34.
Say that again.
0.34.
0.24. Is that 3.4? Okay, I think it should be something greater than 1. Okay, but you got pi there too. 20 times pi. 20.4 times pi. 1.07. And that would be units, centimeters per second. Okay? All right, let's see. Oh, that's what they got in the book too. Good for them. Now, I don't know if I've mentioned this for you before, but let me say it again. If I haven't, I'll say it the first time, but if I have, I'll say it again. After every example in the text, there is something they call a checkpoint, which does a similar type problem, similar type approach and everything. And I think one of the best ways to study is this type material, when you have an author like this one, is as soon as you get out of class and have some free time, you may want to eat lunch next or something like that, but if you have some free time, go to a classroom, go to the library, go to the cafeteria, go somewhere and try to do the checkpoints that we followed the examples we did. And that way, while it's fresh on your mind, do the checkpoints. If you can't remember how to do it, then, if you'll notice right by every checkpoint, it says audio video solutions in English and Spanish are at larsonprecalculus.com. An absolutely free website. You don't need a passcode. You don't need a class code. You don't need anything. Everybody in the world can go to that website if they want to. Of course, it doesn't make a lot of sense unless you have the book, and you can do those checkpoints. The homework is good too. Do the homework too, but the checkpoints are very, very similar to the problem we just did. And Gavin is here. Okay. We're only missing Chris. So hopefully he'll be coming here. All right. So any questions on example 6? All right. Now, if my memory's right, they don't do example 7 either. So let's just clear. Everybody got this one? Okay, let's clear that ink and let's do example 7. All right. What we have now is a wind turbine. Okay. Now, we don't have many of these around here. I don't know, have y'all ever seen a wind turbine? When we were, my wife had professional meetings near Salt Lake City. It was in Park City or something like that, near Salt Lake in Utah. It was a couple summers ago, and it was right at one of our breaks, so I got to go with her. And so we took a little extra time and drove around to see some other things. We went to Yellowstone again. We'd been there before. This is one of our favorite places to go. And we drove through parts of Idaho. Can't remember if we got into Montana some. No, I know we went into Wyoming. So we went through some of the rural areas. We took back roads and stuff just to see the part of the country we don't usually see. And they had wind farms. I mean, just the whole hills. And the wind just always blows across the plain there. And they had these up there. And guess what? They sit so high up there that the farmers are down there cultivating their whatever they're growing down there, getting up hay or whatever. The wind turbines don't bother them at all because they're way up high. And so they're still using the land, but they're leasing the land for the wind turbines. So it's a pretty good deal for them. And it's generating quite a bit of electricity. So it was pretty impressive to see. Okay, let's move on. The blades of a wind turbine are 116 feet long. So I'm going to try to draw a wind turbine here. my drawing's really steep. Okay, there's a blade, there's a blade, and there's a blade. They're supposed to have a little more tilt to them than that. But the blade is, each one of these is supposed to be 116 feet long. And they do look pretty long, so that's pretty good. The propeller rotates at 15 revolutions per minute. Now, they don't show the direction. I'm just going to put it clockwise just for nothing else. So this is going at 15 revolutions per minute. Now, I wrote it that way for a reason. Usually we say that RPMs. That's what it stands for, revolutions per minute, RPMs. Okay? The first question says, find the angular speed of the propeller in radians per minute. So the A is the angular speed of the propeller in radians per minute. And if you remember the slide that I showed at the very beginning, but we had talked about last time, what we're looking for is omega. That's the angular speed of the propeller in radians per minute. Now, units are important, so I'm going to write that down. Radians per minute. Okay? Now, what do we mean as a revolution per minute? One time, all the way around, 15 of those in a minute, right? Now, one time around is how many radians? 2 pi. So 2 pi radians times 15. 15 revolutions a minute, 2 pi radians each revolution. So that is 30 pi radians per minute. That's all there is to it, because the revolution is 2 pi radians per revolution. So we have 15 revolution. I do a lot with units, okay? They're really helpful. They're your friends. Be kind to them. And that's 2 pi radians per revolution. So the revolutions go out, and that gives you 30 pi radians per minute. Without having to do a formula or anything else, that's just what it is. That's how you get radians. That's your angular velocity. 30 pi radians per minute. Right? So that was the A part. All there was to it. Okay? They do some other stuff, but, you know, and they get the same answer. And basically do the same thing. But using units are really helpful. It says find the linear speed of the tips of the blade. So what is, I have it going this way, what is the velocity here? The linear speed of the tips of the blade. Now, for those who were here last time, when we did the slide, let's go back to that slide. Where is it? It's in, here it is, okay? When we were doing this, I pointed out to you, as long as theta is measured in what units? Radians. What is your arc length? Want to remember that one? Okay. Let's go back another couple of, right here. What's your arc length? R times theta. R times theta. As long as the theta is in radians. You can't be in degrees. If it's in radians, the arc length is R times theta. Okay? So let's go back to this one. And instead of arc length here, we put, and what was that arc length? R times theta. Okay? Over T. Okay? Now, what is theta over T? Little omega. That's that. So, therefore, your linear speed is R times your angular speed. Now let's go back to this problem. And we just got our omega, 30 pi radians per minute. And we know our r. Boy, this is simple, isn't it? We know that linear speed is equal to r times angular speed. So that would be 116 feet, that's your r, times 30 pi. Now, radian really isn't a unit, remember? It's just it's a ratio, so it's not really a unit, and this is per minute. That's really the only unit you have there. So what do we have here? Pull out your calculator. I can do it, I think, in my head. That would be a 0, 8, 4, 3,480 pi feet per minute. Well, that's pretty fast, okay? That is very, very fast, okay? And if someone wants to punch in what pi is, that someone got a calculator? 3,480 times pi, 3.14. 161, blah, 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 blah. Someone give me an answer? Help me, help me. Say again?
I don't have a calculator.
Okay. 10,900 and what? They got 33, so something around there. Huh? Yeah. Feet per minute. You know what? I don't want to tilt at that windmill, okay? That is moving. That would chop your head off pretty easily, okay? But of course, they're way up there. That's not going to happen, okay? But now I have heard a few people gripe about birds flying into them because they may be in patterns. But, you know, most of the time they're making enough noise, I think birds don't usually fly into them. Or maybe those are the birds that we need to eliminate from. No, I'm just kidding. Natural selection, whatever. Okay. And again, there's a checkpoint right there. So shortly after leaving class, whenever you can find some free time, a nice place to do it, do the checkpoint. If you can't get what you feel like is a reasonable answer, or you don't know if you got the right answer, you can go to larsonprecalculus.com and see an audio-video solution. What's that? Yeah, it's still in 4.1. We're almost at the end. Here's the last thing in 4.1 we're about to do right now. And we already did the slide because I didn't realize it skipped 2 things. But here, sector of a circle. And arc length is the sort of like the perimeter of the circle, the circumference of the circle, the portion of that, or of any curve, okay? A sector of a circle is an area, a region, okay? So a sector of a circle is a region bounded by 2 radii of the circle and the intercepted arc. So it's the space in between those. Whereas the arc length is just the length that goes along the circle. This is the actual area, okay? And we went through this before. So that's your theta, there's your r, and the formula for this, and we talked about it last time, is A is equal to 1/2 pi r squared theta, okay? 1/2 r squared theta. Now, theta measured in radians. Most of the formulas in this section of this book, in fact, most of the formulas you'll have that have thetas in them, assume to be radians. Don't ever use degrees there. You have to get the radians first. Okay? Now, the way I kind of remember this is r is the radius and r theta is the arc length. So it's 1/2 the radius times the arc length. Not that that really makes any sense, but it kind of does. If you imagine it's like a triangle base, and kind of like the height, 1/2 the base times the height. So that's how I remember the formula. It needs to be in square units, and r would be square units. So I'm squaring the r. Theta in radians has no units. So yeah, that makes sense. Okay? So, let's do example 6, which they don't show. So we'll do example 8. The area of a sector of a circle. What we have is a sprinkler on a golf course, okay? What a waste of water. I'm sorry, I didn't say that, okay? Sprinkler on a golf course shoots out water about 70 feet, okay? And it rotates through an angle of 120 degrees. I'm just going to estimate this would be the angle of 120 degrees, okay? And it does 70 feet over that, so it's spraying a region like that, okay? And they show here that's sort of the fairway here, and you're just watering the fairway, okay? The question is, find the area of the fairway watered by that sprinkler. Okay? How would we do it? You've got to change that degree. There's the formula right there, but don't plug in 120 for your theta because that's in degrees. You've got to get it to radians. So how do we get 120 degrees to radians? Okay? And what was my little rule? Put the units in their place. These two blanks here, this is for numbers, that's for units. Always put the units in the place. What unit goes where? Say again? Radians on top, degrees on the bottom. And then match the numbers with that. How many radians are equivalent to how many degrees? 180 degrees is equivalent to how many radians? Say again? Pi radians. Remember, yeah, okay. Pi radians is 180 degrees. Now the degrees will cancel out, and in fact the zeros can cancel out, and 12 will go into 18, or what will go into 12 and 18? 3 will. That would be 4 times. That would be 6 times. What will go into 4 and 6? 2. That would go 2 times. That would go 3 times. So that would be 2 pi thirds radian. 2/3 pi radian. Okay? So now you got your theta in radians. Now you can plug in the formula. 1/2, 120, no, 70, duh. Okay, 70 feet. But you got to square that and then multiply that by 2/3 pi radians. Okay? Now, I don't care what order you do, but just for funsies, the 2's can go out, and that just gives you 70 squared, which is 4,900 times pi divided by 3. That's just going to be something a little bit less than 40. It'd be about 4,800 or so. Because, I'm sorry, a little bit more than that. A little bit more than 5,000 square feet. What do they get in the book? Or you do it on your calculator? 4,900 times pi divided by 3. Anyone got it? Anybody? 4,900 pi divided by 3. Second? A little bit more than 5,000. How much? 5,131. And 31, is that what you said? Yeah, 31. Let's leave it there, and they'll call those square feet. Okay. Keep your units. You not just you square the number, you also square the units, so that'll be in square. Yeah, that makes sense. Now, if you wanted to figure out what portion of the acre that was, you could do that. I don't keep those conversions in my head, so you'd have to look it up somewhere. But yeah, pretty wide area that's covered. Okay? Any questions? All right. And there's a checkpoint following each of the examples in the book, and you can do that, I'd say, at your earliest convenience. Make sure you got that down, and you can check it at larsonprecalculus.com. That finishes 4.1. So let's do the vocabulary at the top of 4.1. I don't know if any of you have your books, but I'll read them to you. Two angles that have the same initial side and the same terminal side are blank. Co-terminal, same terminals, same terminal side, exactly. Number two, the blanket near the beginning. One blank is the measure of a central angle that intercepts the arc length equal to the radius of the circle. That's a radian. That's how we define a radian. Okay, one radian is a measure of the central angle that intercepts an arc length equal to the radius. Okay, because radian is a ratio of arc length to radius. So if that's one radius as arc length, that gives you one radian. Number three, two positive angles that have a sum of pi halves are blank angles. Complementary. And two positive angles that have a sum of pi are supplementary angles. Excellent. Number four, the angle measure that is equivalent to the rotation of 1/360th of a complete revolution around an angle's vertex is 1 degree. 1/360th of the way around is a degree. Yeah. 1 degree. All right. Number five, the blank speed of a particle is the ratio of the arc length traveled to the elapsed time. Hint here, length per time. Okay. Linear speed. Length, linear speed. Okay. And the blank speed of a particle is the ratio of the change of the central angle to the elapsed time. Angular velocity, exactly, or angular speed, right. Number six, the area of a sector of a circle with radius r, central angle theta, theta measured in radians, is given by the formula what?
Is it half radius squared times theta?
Radius squared, yeah. 1/2 r squared theta, exactly. 1/2 the radius squared times the angle. In radians, be sure you got that. Homework exercises here, I've given these before, but again, any of either 7 or 9 or both. Okay, both of these are located at calcchat.com if you have trouble with them. Number 11, and by the way, their answers are in the back of the book too. The odd numbers have answers in the back, and if you can't figure out how to get that answer in the back, go to calcchat.com, and they have worked out solutions for the odd number, and tutorial help and worked out solutions. So 7 or 9 or both. Do 11, it has 2 parts, A and B. It's at calcchat.com. Do 13, it has 2 parts, A and B. It's at calcchat.com. Do 15, it has 2 parts, A and B. It's both at calcchat and calcview.com. And by the way, they have these little QR codes here. I think that's what they're called. If you got a smartphone, you can just show that to it, and it comes up. It pulls it right up, so you can see it on your screen. Okay, then do any of the odds, well, either 17 or 19, and they're both at CalcChat. 17 is at CalcView. Do either 21 or 23, they're both at CalcChat, neither are at CalcView. Do 25, it has 2 parts, it's at CalcChat. Do 27, it has 2 parts, it's at CalcChat. Do 29, it has 2 parts, it's at CalcChat and CalcView. And then do either 31 or 33, they're both at CalcChat, but 31's at CalcView. Do 35, it's at CalcChat and CalcView. Do 37, it's at CalcChat and CalcView. Do either 39 or 41 or both, they're both at CalcChat. Do either 43 or 45, they're both at CalcChat. Do 47, it has 2 parts, it's at CalcChat. Now, we didn't do any like that as an example, so I think they're pretty easy to figure out. If you have trouble, ask me, bring them to class, and we'll do one of those there. Same thing about 49. It has two parts. It's a calc chat, so you can look at calc chat, and I think they'll describe it pretty well. Do 51 is a calc chat and calc view. Do 53 is a calc chat. Do 55 is a calc chat. Do 57 is a calc chat and calc view. Do 50, well, you know, I kind of don't like the error analysis ones. When I see error analysis, I think, you know, determining the error that you may have made. This is, they've done a problem wrong and you figure out what they did wrong. So I don't like going through something that's wrong, you know. I'm afraid that gets embedded in your mind, not the right answer. So do that if you feel comfortable with it, 59. It should be at calc chat. We didn't do any like this, but this is pretty interesting example. Number 61. It's a calc chat, so you can do those. Sorry. My head is clogging up on me. I'm having trouble breathing. And then I would say 63 is a pretty decent problem. It's a calc chat. Linear and angular speed, you can do either 65 or 67. They're both a calc chat. There's an area problem, 69, that's available at calc chat. And then there's a couple true false, 71 and 73, and I think they should be at calc chat. The 75 is a writing problem. You can read through it, think through it, and if you want to somehow get a paper out of that, you can use that as your paper topic, but it doesn't seem very exciting to me, but it may be to you. There's a think about it, 77 you can look at. There's a proof if you're interested in that. Okay. What's that?
Putting on the problems on Blackboard?
They're on in Blackboard under the YouTube videos. I'll put the links there when I get a chance, but it's you can probably find the YouTube video. It's not there yet because I'm recording it right now, but it will be there probably this afternoon, probably before 1:15. If I have a chance to upload it by then, I'll try.
What page is that?
It's pages 267, 268, and 269. Second? Okay, now you can log into WebAssign. Did you get the code last time? Okay, you can log into WebAssign and do similar problems on it. Okay, you use this? Did you use this code? Okay, do you have the code that came with when you purchased? You did Cengage Unlimited. On your receipt, there was a code there. Did you keep the receipt? Okay, did you use that code?
Yes, but when we log into WebAssign, it's just talking about sign in, but I never signed in.
But what?
I never signed in before, so somebody signed in.
It's talking about website account, not Cengage account.
Yeah.
Okay, well, this is supposed to give you both of those. That account, and you type this one in and it wouldn't work?
I mean, WebAssign pops up, but it tells me to sign in. I
You
can't sign
need a
in.
WebAssign account to
You gotta have that. We have website. You have to have an account. We gotta make one.
And this doesn't work for that. The one I gave you.
Yeah, you can use your regular ebook, but you wouldn't be able to go to like WebAssign.
Okay, but this thing they gave me, the Lawson.al 8 digits, that was supposed to be for both the ebook and WebAssign, because the guy said that would work, but it doesn't. You tried this number and it wouldn't work. Okay, if not, I'll have to find out someone who knows more about WebAssign than I do, because he told me this would work for both of them. It's supposed to be the one thing. It's a WebAssign thing. It also works for the other thing too, but
You probably should have an account. It's your first time using website. You have to put the passcode in. You got a passcode for your website?
yeah, that's the thing he gave me that I put on the board last time and this time. That's supposed to be the class code for WebAssign and for Cengage Unlimited.
Okay, so you have to put that in for everything.
Yeah. But in the past, when I've done WebAssign, we didn't have the Cengage Unlimited. That's exactly how that look. Lawson.al and 8 digits. That should be it. If it's not, I'll have to find out what's wrong with it. Yeah.
What tabs do YouTube videos up? Like past YouTube
I'm sorry?
You know the videos you're recording, what tab is my Blackboard?
Okay. I told you before, I haven't got that set up on Blackboard yet. Okay. I hope to get that done. I don't think I'll get it done today because I only have 1 hour of office hours today. But tomorrow I've got 4 hours. I hope to get it finished then. I've got some classes done and some not. This one I just didn't get a chance to do that. But if you are familiar with YouTube, you can probably find it. I've had people say, oh yeah, I found it out there. And they're all there, but there's a lot out there. But I'll get the link that's it's to the playlist in YouTube. Now, even when you get to the playlist, and I told you all this before too, the files at the top are from the last time I taught the course. The files at the bottom are from this time. I don't take these off because periodically, either the server will go down, Screencast-O-Matic won't work, the supercomputer files up, or something like this, and there'll be days I can't record, so I'll leave the others out there so you'll always have one you can go back to. It won't start and stop at the same place, right place, but it'll be pretty close. So that's why I leave them there. So you can go through you don't have to do the ones at the top. Start at the bottom. Those are the ones you've done. But I'll get you the playlist link as soon as I can. I think it'll be Friday. I hope it'll be Friday. I may admit, no, I'm not going to have time this evening either. I was going to say I could do it maybe this evening, but my wife said we have some place we've got to go tonight. Okay. So, any more questions on 4.1? Okay. And if you got your book, so those homework assignments, every section, when you see your book, either e-book or physical book, you'll see little sections, the odd numbers from each little grouping, okay? And if they're in just dark type, that's at Calc Chat. All the odd numbers are at Calc Chat. The red letter type, that's at, and the numbers red letter, that's at Calc View. And the QR code is there. All right. Okay. Let's now go to 4.2. Takes a while for PowerPoint to load. Goodness gracious. All right. We'll start from the current slide. We're still in Chapter 4, Trigonometry. We're now in 4.2, Trigonometric Functions, the unit circle. Now, when I first took trig many decades ago, we always started with right triangle trig, which to me made perfect sense, and then the unit circle followed that, and it made good sense. Nowadays, just about all books start with the unit circle, which is fine. It's a good place to start. But to me, it's not nearly as intuitive as the right triangle trig. But they'll do right triangle trig in 4.3. So let's do 4.2. Right now, we're going to identify what in the world a unit circle is. You make a guess. What do you think a unit circle is?
A circle with degrees and radians around it.
Okay, every circle has degrees and radians around it. What makes a unit circle a unit circle?
It's on the graph.
Okay, what about
It's on the graph.
Okay, on the graph, what makes it a unit circle?
It has points.
Okay, it has points. All circles have points. What makes it a unit circle?
It has radian points.
Okay, yeah, radians and degrees. It has both. Okay, does any of you ever played the card game called Uno?
Yes.
When do you call out Uno? When you have one card left. That's what Uno means. One. A unit circle has a radius of 1. That's what makes a unit circle a unit circle. So we'll identify, we just did, what a unit circle is, We'll describe its relation to real numbers, and we'll evaluate trigonometric functions using the unit circle, especially our favorite ones. We have some favorite trigonometric functions. Well, all the trigonometric functions, but at certain angles, like you were talking about before, degrees and radians. And we'll use domain and period to evaluate sine and cosine functions, and we'll use a calculator to evaluate all the trigonometric functions. So let's start with the unit circle. And again, two historical perspectives of trigonometry incorporate different methods for introducing trigonometric functions. To me, the part that makes the most sense is triangle, right triangle trig. But the other is unit circle. We're going to start with unit circle. So here's the unit circle. There is a unit circle. It's a circle centered at the origin on the graph, like you were saying, with a radius of 1. The radius is 1 all the way around. Now these are obvious points. 1, 0, 0, 1, negative 1, 0, and 0, negative. Those are easy to pick out because you know exactly where they are. But it's not just those points. Every pixel on that circle can be described as a coordinate, xy coordinates. And what's true about this, because it's a circle of radius 1, is that x squared plus y squared is always equal to 1. This defines a circle of radius 1 centered at the origin. Okay? So that's going to be true. We're going to come back and use this formula several times in the future, so remember, to be on the unit circle, the xy pair has to fit that criteria. The x squared plus y squared is equal to 1. Okay? Now, just a little hint. What are the domains and ranges for the x's and y's? What values can x take on? Sort of see it here. Any point between negative 1 and 1 can ever be 2, 1.3. Never. Always between negative 1 and 1. How about the y's? Between negative 1 and 1. Can't be 1.72. Can't happen. Or negative 1.1. Can't happen. It's got to be between minus 1 and 1. Just as that. The x's and y's are always less than or equal to, or between minus 1 and 1. Always. Okay? Just a note. So, now what we're going to do in thinking about the unit circle and things here, it's really what we were doing before, but it's a weird way of doing it here. Imagine wrapping the real number line around that circle, with positive numbers corresponding to counterclockwise wrapping, negative numbers corresponding to clockwise wrapping. Okay? Basically, you're talking about arc length, just like we did before. That's all this is you take a number line, wrap it around here, you're talking about arc length. That's exactly what you're doing. Okay? But then these measures here, and by the way, this looks like this is in quarters. It looks like 1 quarter, 1 half, 3 quarters, and 1, because that looks to be just about the same as a radius. Now, they don't say it is, but in my mind, that's what it is. So these are positive t's this way, negative t's that way. Wrapping that way. Okay? Now, I don't find this really all this helpful, but if you do, that's what's happening. Okay? As the real number line wraps around the unit circle, each real number t corresponds to a point xy on the circle. Every real number t on that number line, in other words, the arc length corresponds to an xy ordered pair. And the x's and y's are between minus 1 and 1, both of them. For example, the real number 0 at the base down here, that corresponds to this point, 1, 0. We picked that one out. Moreover, because the unit circle has a circumference of 2 pi, the real number 2 pi, when you go all the way around, wrap it all the way around, that circumference of 2 pi, you're right there back at 1, 0 before. Just like we said before, okay? There's nothing new here except they're picturing a real number line wrapped around the circle. which is just your arc length. Okay? In general, each real number t, they love using that, corresponds to a central angle theta, whose radian measure is t. So why call it t? Why don't you call it theta? I don't know, but they do. Except t measures a length and theta measures an angle, but they're the same number, okay? And it's just here. With that interpretation of t, the arc length formula then is S is equal to R theta, okay? That is exactly what we used before, as long as theta is measured in radians, of course, okay? But there's no t in this equation. You could either put the t here, and that's really what they're doing, but your R is equal to 1, right? Because it's a unit circle. And if R is 1, t is equal to theta, which is exactly what they say here. S is equal to t. I mean, whatever you want to call it. Indicates the real number t is the directional length of the arc intercepted by the angle. It's the arc. Just like I was saying, it's the arc length intercepted by the angle theta, given in radians. Okay? So I don't know why they did put t here since they're big on it, but they keep S. It's still true. Everything's still true. S and t are measuring the same thing. Now, let's talk about the trig functions then. The trigonometric functions. There are 6 of them, and only 6. You're probably familiar with them already. From the preceding discussion, it follows that the coordinates x and y are 2 functions of that real variable t. However far you've gone in your angle there, that determines the x depends on that, the y depends on that. Okay? You can use those coordinates to define these 6 trigonometric functions of that angle or real number t. Okay? Now, seldom will you ever see them spelled out this way, but they're spelled sine. And why they put them, I know why they do, but I always think of sine, cosine, tangent, cotangent, secant, and cosecant. They put them in this other order, and there's a reason for it, but you haven't gotten there yet, so why confuse it? Sine, cosine, tangent, cotangent, secant, cosecant. Those 6 functions are normally abbreviated sine, cosine, tangent, cotangent, secant, and then you can't do the same thing here. Why not? That's the same as cosine. So what they do here, rather than the first 3 letters, is first 3 letters, 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 and first 3 consonants. Leave out the vowels. CSC. So that one is CSC. All the others are first 3 letters in the word. And that's how we'll always do it. Now, it looks like sin, but it's sine. Okay? Always sin. And you don't usually say cos, you say cosine. You know, you just read them. Secant, tangent, cotangent. Those are the abbreviations. Okay? Now, here are the definitions. These are the definitions when you're dealing with a unit circle. And that's sort of the problem with this, doing the unit circle first. You get used to this being the definition, and later when you go to bigger circles or smaller circles or right triangle trig, they have slightly different definitions. Whereas if you did those first and then came to this, you just substitute basically your hypotenuse is equal to 1. Now, we haven't even talked about what an hypotenuse is, but that's what you get.
The longer side of the triangle.
What's that?
The longer side of the triangle. You say hypotenuse, the longer side of the triangle.
Of a right triangle, exactly. Of a right triangle, you're absolutely right. That is the hypotenuse. And let's see if one of the figures we had before. Yes. If you think of this, this is your starting, there's your initial side, terminal side, the angle in between. Okay? If you dropped a perpendicular here, this would be your x value, this would be your y value, okay? And this would be your hypotenuse, right? X, y, and always 1. So if the x is less than 1, the y is less than 1. Could be equal, but most of the time less. So your long side is always 1. And to me, that's where you ought to begin. I would even put the ones in there. But they don't. They just say this. And a lot of people will then later, when you're dealing with other things, say, oh, the sign is 1. The sign is the y value. Only on the unit circle is it the y value. Okay? It's related to the y value, but it's equal to the y value only on the unit circle. If they said y over 1, that makes more sense. It may not make sense looking at it here, but that's what it is. So on the unit circle, your sine is always the y value, your cosine is always the x value, your tangent, and get used to this because this is going to come up later, is the ratio of the sine to cosine. So it's the ratio of y to x, y divided by x. But here we have a problem, Houston. Okay? On the unit circle, x is 0 up here and down here. X is 0 at both of those places. So you can't define your tangent up here or down there. Undefined. Tangent is undefined there. It's defined as y over x only when x is not equal to 0. Okay? And I go on this way. Cotangent is then the reciprocal of tangent. Okay? It's cosine over sine. So it's x over y, but now your y can't be 0. Y is 0 here and here. So you can't have those values for cotangent. And then we get the secant, which is 1 over the cosine. So it's 1 over x. Okay? And, but again, has the same restriction tangent does, x can't be 0. So it's not defined here and here. And then cosecant is 1 over sine, which is 1 over y, and it can't be, y can't be 0, which would be here. So those values have no cosecant. So cotangent and cosecant have the same limitations. Y can't be 0. Secant, tangent, secant. Sines and cosines are defined everywhere. Everywhere. No problem at all. Okay? And they're defined to be y cosine x. On the unit circle. Only on the unit circle. So, those definitions of trigonometric functions note that the tangent and secant are not defined at x equals 0, and similarly the cotangent and cosecant are not defined when y is equal to 0. For instance, because when t is equal to pi halves, right? Pi halves, y is, your x's are 0 there. So tangent of pi halves, secant of pi halves, undefined. Can't ever do it. Okay? Same thing with 3 halves pi or negative pi halves. Cannot happen. Similarly, the cotangent and cosecant are not defined. Y is equal to 0, and that's at any multiple of pi. Okay? At 0, at pi, at 2 pi, 3 pi, 4 pi, 6 pi, negative pi, negative 2 pi, negative 3 pi. Any of those values, cotangent, cosecant, not defined. Okay? Because your xy pair there is either 1, 0 or negative 1, 0. Y can't be 0. Make sense? All right. Hang on to that concept when we get to 4.5, when we start, or 4.6, somewhere in there, we start doing graphing. That will come back and haunt you. Okay. So, in this figure, we show some of the special angles, some of the special points on your unit circle. Okay? In this, we're going to divide the unit circle into 8 equal arcs. Okay? 8 equal slices. Pizza! Think of pizza. Okay? Now, we'll have one cut here, one here, one here, and one there. Okay? So you have 1 slice, 2 slice, 3 slice, 4 pieces, or whatever. Okay. Now, 8 equal pieces. Now, how in the world did they come up with these XY values? Here's why. Okay. To get 8 equal pieces, okay, think of this. 1 trip around the circle is how many? 2 pi. Half a trip around it? Okay. And half of that?
Over 2.
Okay, pi over 2. Now, to get half of that, we draw the line that is exactly bisecting 90 degrees, or pi halves. Okay? That is your one-to-one line, right? Y equals x, right? Is that true? Because however far you go here, you go the same distance here. Y equals x. There's the key. That line right there is this line. Let me get my pen darkened. This is y is equal to x, right? Now, remember what happens, what's true about every point on the unit circle? What formula is always true? For every xy pair on the unit circle? I said it early on. Ah, there it was. X squared plus y squared has to equal 1. That puts it on the unit circle. So let's go here, and if y is equal to x, that says x squared plus, but y is equal to x, so that would be, well, I'll put y squared is equal to 1, but if y is equal to x, that says x squared plus x squared is equal to 1, because y is equal to x, right? Agreed? Okay. Can you combine like terms there? What does that give you? Add x squared plus x squared, what do you get? 2x squared is equal to 1. Let's solve for x. Divide by 2, and that gives you x squared is equal to 1/2. And then what would we do? Solve for x. Square root of both sides. X equal plus or minus, okay, the square root of 1/2, which is, by the way, the square root of 1 is 1, and the square root of 2 is the square root of 2. Now, we're only going to deal with the plus one, so I'm going to leave off the minus for now. But you see, the minus is just going to be down here. So it's still there, but let's leave it off for now. Okay? A lot of time, in fact, we'll take off the plus 2. A lot of times people really don't like having a radical in the denominator. In the old days, which I remember, there was a reason for that. Okay? And when I say in the old days, that was before computers and before calculators. Back then, you had to do everything by hand. Okay? Now, if you were trying to do 1 divided by the square root of 2, you'd have to look up in a table and see what the square root of 2 was. And depends on how many digits, because that's an irrational number, so there's not a nice fractional form, so you have to stop writing digits somewhere. So most of the time they write maybe 4 digits, maybe 6, something like that. I don't remember what it is. I know it's 1.212 blah, 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 blah. But it doesn't follow that pattern. That only the first 4 digits are like that. The rest of them. In fact, if someone has a calculator, punch in what the square root of 2 is. Square root of 2. Oh, wait, 1.414? Oh, I'm sorry, I wrote it wrong then. 414. I was doing the other thing, sorry. All right, get it back. Okay, say again, well, 414. Keep on. 2, 1.
3, 5, 6, 2.
Okay, that's as far as your calculator goes. It goes on forever, never repeating any pattern whatsoever.
Say 4.
Say again?
Behind 2. Say 4. Behind 2. Behind the number 2.
Okay, say 1 point.
No, you know all of the way. All the way to the end. You have to add 4.
Add a 4? Okay, you have one more digit on your calculator. Okay, fine. So let's do 1 divided by that. That would be 1.4142135.624 divided into 1.00000000000 however many, and then you move this decimal 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 places. Move this one 1, 2, 3, 5, 6, 7, 8, 9. Hey, I got the right number. 10 places. And start your division. Long division by hand. You're going to be occupied for a while, aren't you? Okay? Now, did you just do it on your calculator? I just saw you punch yourself. Okay. That's how we had to do it in the old days before calculators. Now, I'll give you a hint. That's why they didn't like having radicals in the denominator. So what could you do to get that radical out of the denominator? Multiply by root 2, but also multiply the numerator by root 2. And what does that give us? The square root of root 2, and then root 2 times root 2 is 2, and that's exactly what we've got here. Now, why was that better? Because try doing this division. 1.41421356624. Divide that by 2, and I can do that in my head. 7, 0, 7, 1, 0, 6, 7, 8, 1, 2. Okay? Which would you rather do? Long division this way or long division that way? That way by sure. You rationalize the denominator. Now, why doesn't this make any difference anymore? No one does long division. They use your calculator. So it doesn't really matter how you say it. You could have said this is 1 over root 2, 1 over root 2. But because mathematicians do things the old way, we put it as root 2 over 2. It doesn't matter. That's the number. Okay, that's what the x is. And because you know the y is equal to x, that's what the y is too. Okay? So that's where those numbers stand from. So this one down here is minus root 2 over 2 minus root 2 over 2. This one over here is the minus root 2 over 2 on x, but positive root 2 over 2 on y. This one over here is positive root 2 over 2 for x and minus root 2 over 2 for y. That's where you get these points. Okay, let me get all this chicken scratch off of there because we don't really need it anymore. But that's where they came up with those points. And by the way, as I just said, root 2 over 2 or 1 over root 2 is 0.707 blah, 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 blah. Okay. That's the approximation to it. Okay. Now, what t-values are also theta values or s values, whichever you want to call it, because r is equal to 1, would that correspond to? Here is 0, here is pi fourths, pi halves, 3/4 pi, pi, 5/4 pi, 6/4 pi, which is 3 halves pi, 7/4 pi, 2 pi, and on and on and on. So that's where those t values or theta values or s values come from on the unit circle. Those are all correspond to the same thing. Okay, that's what they do. So guess what? We now know the sign of pi fourths. What was sign? The y value. There it is. Cosine of pi fourths. The x value. There it is there. And what was the tangent of pi fourths? Y over x, and this over that is 1. The cotangent, 1. The secant, okay. Secant, 1 over. Okay, now, here is where it's easier to do it the other way. Okay? If you had written this as 1 over root 2, 1 over root 2. Because now when you reciprocate that, what do you get? Root 2. So the secant is root 2 and the cosecant is root 2. 1 over the x, secant is 1 over x, and cosecant is 1 over y. So this is okay on some, this is better on the secant cosecant when you reciprocate. Because that's so much easier to do.
Would it be 2 root 2 over 2?
What's that?
Would it be 2 root 2 over 2 for the, like the secant or the cosecant?
You could say 2 over root 2, but yeah, then you would
2 root 2 over 2.
Yeah, yeah, okay. So you do 2 over root 2 to be the secant, right? Now you rationalize that, and that would be 2 root 2 over 2, and that would be root 2. See? This becomes a 2, and 2 over 2 is 1, and you're left with root 2. Yeah. That's the long way to do it. The short way is do it 1 over root 2 and reciprocate that. Okay? Can you tell me the sine of pi halves? 1. Cosine of pi halves? 0. The tangent of pi halves? 0. Yeah. Huh? Undefined because you can't divide by 0. Yeah. Okay. Very good. And you can do all the way around the circle. Do it. Are we out of time? How sad. Okay. Oh, I have my watch in my pocket. No wonder I didn't pocket. Let's see. We got a little ways in 4.2. Let's do some homework exercises there. I think you can do 5 or 7 or both. You can do 9 or 11 or both. Oh, wait. Do 9. Yeah, do 9. Don't know if you can do 11 yet, so we'll stop there and pick up. And go from there. But you have a whole bunch. Yeah, 5 or 7 and 9. Okay. And what's that? It's going to be on YouTube video. Okay, and that will be on Blackboard. I'll get the link and you can listen to that. Okay. All right. But it's always going to be the same. It's going to be the odd number exercises at the end of the section. Groups of those. You choose which ones you want. All right. Good deal.